Howdy class, for the first exam review, we're going to start with a question on a flash distillation. In this problem statement, we're given a stream of 50 kilomole per minute of 70 mole percent methyl acetate, and the balance methyl ethyl ketone goes into our flash column at 100 degrees C and 3 atmospheres pressure. We're asked to find the outlet flow rates, our V and our L, our outlet compositions, the YA and XA, and the percent recovery of the methyl ethyl ketone in the liquid. For our thermodynamic data, we're given the Antoine coefficients with the Antoine equation in natural log and temperature in Celsius. So first, we want to start by finding our outlet compositions. From this, we remember from our formula sheet or our thermo class that XA is equal to P minus PB sat over PA sat minus PB sat. This equation will be given to you on the formula sheet. However, if you forget and you want to derive it, this comes directly from Raoult's law. With Raoult's law, we have XB PB sat equals YB P. We can replace our XB and our YB with our 1 minus the A composition. So we get PB sat 1 minus XA equals P 1 minus YA. We distribute through, and we get PB sat minus PB sat XA equals P minus P YA. From the Raoult's law on our A species, we have XA PA sat equals YA P, which is exactly what we have here. So we can replace this and get PB sat minus PB sat XA equals P minus XA PA sat. Then collecting our XA-like terms, we have XA, PA sat minus PB sat equals P minus PB sat. And dividing everything over, we get our XA is equal to P minus PB sat over PA sat minus PB sat. Okay, this guy. Oh, it's green. Okay. Howdy class, for this first exam review, we're going to go over a distillation. Howdy class, for this first exam review, we're going to go over first an example of flask distillation. In this problem, we're given an inlet stream of 50 kilomole per minute, 70% mole percent methyl acetate, 30 mole percent methyl ethyl ketone. This goes into a flash distillation column at 100 degrees C, 3 atmospheres. And we're asked to find the outlet flow rates, V and L, outlet compositions, YA, XA, and the percent recovery of the methyl ethyl ketone in the liquid. For our thermodynamic data, we're given our Antoine coefficients for our A species, which is the methyl acetate, and our heavier species, the methyl ethyl ketone. And we're given this form of the Antoine equation, which is our natural log and temperature in Celsius form. So first, we want to go ahead and find the compositions. For the composition, we look at the back at our formula sheet, and we find XA equals P minus PB sat over PA sat minus PB sat. This should look familiar to you from your Thermo 2 class. However, if you want to rederive this, it's easy to derive just from Raoult's law. With Raoult's law, we start with our B species, XB PB sat equals YB P. We change B's for A's, so we get PB sat 1 minus XA equals P 1 minus YA. We can go ahead and multiply in PB sat minus PB sat. XA equals P minus PYA. This should look familiar as the right-hand side of our Raoult's law for our A species, where we have XA PA sat equals PYA. So we're going to go ahead and replace that there to get rid of our YA. We have PB sat minus PB sat XA equals PA sat XA. Following that, we're going to add this to the other side, subtract our PB sat over to collect like terms, yielding XA times PA sat minus PB sat equals P minus PB sat. Finally, we divide everything over, and we get this equation right here. Our XA equals P minus PB sat over PA sat minus PB sat. Now that we've done this quick little review of thermo, we just need to find what our PA sat and PB sat is. We're at 100 degrees C. We don't need to convert that. And so our PA sat is equal to the exponential. We plug in our coefficients down here, 14.2456 minus 2662.78 over 100 degrees C plus 219.96. And this comes out as 37.1 kPa. One thing to make sure of whenever you're using Antoine's equation is that you know what units everything comes out in and what temperature you're supposed to plug in. They can vary between Celsius, Kelvin, vary between atmospheres, PSI, kPa. For this one, this is a kPa formula. Doing similarly, plugging in the values for our MEK, we get 186.3 kPa. Finally, we have everything that we need to plug into this equation. We get XA is equal to our pressure, which is 3 atmospheres. We need to convert that to kPa. So we have 3 atmospheres. Our conversion is 101.35. We subtract 186.3. And then on the bottom we have 371.1 minus 186.3. This gives us an XA value of 0.637, which we can go ahead over here and fill in. Finally, we need to find our corresponding YA. For this, we can just use Raoult's law, where we have YAP equals XAPA sat. This gives us YA equals XAPA sat over P. So this is 0.637 like we just got. 371.1 over our 304, which is this 3 times 101. And this gives us a YA value of 0.778, which we can go ahead and fill in here. Next, we want to turn to looking at our flow rates. For this, we're just going to do simple mass balances across our tower. So we can write our mass balance for our A species and our total mass balance and solve those together. For our A species, we have XFF is equal to XAL plus YAV. That's our flow is equal to our liquids plus our vapor. And correspondingly for our total mass balance, we just have F is equal to L plus V, which we can solve for either L or V. We'll just do V and give V is equal to F minus L. Once we have that, we can plug into our first one. We have XF of F is equal to XAL plus YA, F minus L. We can go ahead and expand this in and collect like terms. So we're going to subtract this YAF to the other side and get that we have F XF minus YA equals L times XA minus YA. So finally, we solve for the L that we want. We get L is equal to XF minus YA over XA minus YA times our inlet flow rate. Once we have this, we can plug in all of the values that we know. We have XF is 0.7. Our YA is 0.778. Our XA is 0.637, and the same 0.778. And we multiply this 50 kilomole per minute. And we get a final answer as 27.7 kilomole per min, which we can go ahead and write over here. Finally, just using this equation again, we have V is equal to F minus L which just gives us 22.3 kilomole per min. And we can go ahead and write that up here. Lastly, we want to do the recovery. For our recovery, this is just how much of our total methyl ethyl ketone ends up in our liquid phase. So for that, we're going to have, this is just equal to XBL. This is the total in our liquid phase over our total amount, which is XB flow times F. And so we can write this out as 1 minus 0.637 over 22.3 over 0.350. Plugging this into a calculator gives 54.1%, giving us the last thing that we needed to solve for. So flash distillation examples are pretty simple. It's just applying what you learned in Thermo 2, equilibrium with Raoult's law, but in the context of a mass operation, a separation like this. Everything just follows your Raoult's law equilibrium, and you can solve everything from there.